Hello everyone, my name is Utkarsh Verma. I am from Muzaffarpur, Bihar. Currently, I am pursuing the Bachelor of Technology from Indian Institute of Information Technology, Ranchi in Electronics and Communication Department. I had selected as an intern in Emertex company in the batch named 26 Cortex 2 Embedded System. In this internship, our main goal is to create a prestigious project whose name is on our slides, that is EV and ADAS system. EV stands for electric vehicle and ADAS stands for Advanced Driver Assistance System. In this project, we will know about how the electric vehicle without the driver we can be get the safe from every things. In this project, we will use the three things. First, the platform, simulator, and framework. These three things get the helpful for successfully execution of this project. In this platform, we use the platform as a blue pill that is written as the STM32 F103C86. We use the simulator for simulating all the parameters in the Pixim lab. And third, we can generate the code from STM32 Cube IDE. We start to generate the code from STM32 ID. We make the binary file of that such code and then send to the Pixim lab. In Pixim lab, we can choose the blue pill as the one of our microcontroller and then we simulate and obtain the results in the IO virtual term. And after when we obtained the results in the IO virtual term. At the last, we integrate all the IO virtual term in the Python dashboards to obtain the final outcomes and result of that project. And we are successfully executed this thing. So in this project, we are creating the 11 slides for our project to show their results and understanding the concept of our project, how we can proceed the project, how much phase we are needed, what the requirement, what are the things we are using. So everything including the tool and everything we need. So just move on the second slides to understand the system architecture of overview of our projects. So there is the system architecture of overview. It's mean that there is a flow of the projects. In the flow, we use the sensor. Then we forward these projects into the STM32 Blue Pill, which is the microcontroller which is present in the Pixim lab. And then we use the UART for making the serial communications between the IO virtual drum and the Pixim lab. And after all, we obtained the result from the Python dashboard. So we use such type of system architecture and this is the flow of our project. So here what the sensor use, how we can use the STM32 blue pill and everything just focus we present in the slide number 2. First we talk about the sensor. So in sensor we use the potentiometer which is present in the Pixing lab. So this potentiometer is further classified into the four parts that shows the acceleration, brake pedal, temperature, and SOC. SOC stands for the state of charge. So these four sensors we need for creating the for providing the some supplies and values. So in the industry purpose, they can use the um, um, some particular ARM processors, but here we can't be take this hardware implementation of such projects, so we can use the sensor as a potentiometer and you and provide the some uh, values to the IO virtual term. In second, we can give the STM32 blue pill. In this, we created the EV controller and ADAS engine fault handler. In the third UART, we find the UART that is the serial communication, that is a uniform asynchronous receiver and transmitter with the fixed value of 1,15,200 bps. In this we can be combine all the things and at the last in the Python dashboard we we implemented the speedometer, SOC bar, and ADAS bird eye and everything. So these are the flow of our system architecture overview of that projects. So in our third slide, in third slide we have found that how we can implement our project. So our project has been implemented in the 9 phases, from the environment setup to the full real-time ADAS dashboard. It's mean that if for successfully execution of this project, we need the 9 phase to complete of this project. First in 9 phase, here we see, in the first we have used the dev environment. It's mean that the in first dev environment we use the STM32 cube ID plus Pixim lab plus Python setup. It's mean that we just for the dev environment, initially we set up the STM32 cube ID from the STM microelectronics, and then we access this thing. We can generate the every code so in the STM32 cube ID, and after then we create the binary file and bin file from the STM32 and send it to the Pixim lab. In the Pixim lab we have found that there is a blue pill board. In this blue pill we use the STM32F103C8T6 microcontroller. By using this microcontroller we can create the spark parts, and these spark parts create the IO virtual terms. In the IO virtual term, before IO virtual term we can use the input as a potentiometer. In potentiometer we use the acceleration, brake pedal, temperature and state of charge and such things, and after then we generate the simulation on the IO virtual term, and at the last we integrate all the IO virtual term and put the establish the Python setups, and last we put every IO virtual term and can create our project. In the second phase, we make a GPIO and peripheral. GPIO stands for general general purpose input output. So in this, we create the small project on the STM32 cube ID to generate the code and create the setup of perfect setup of STM cube ID. So here in a starting we can use the we can create the small project of the LED to satisfy the every concepts and as well as every setups of the STM32 cube ID as well as the Pixing Lab simulation. In the third phase we use the ADC sensor inputs. In ADC sensor, ADC stands for analog digital conversion. It's mean that in every STM32 cube ID we use that we need the analog values. We need the analog, we give the analog values from the potentiometer as the acceleration, brake, temperature and SOC. But in the STM32 cube ID it's a need to create it need to digital value, but we can get the analog value from the Pixim lab. So we need to convert the analog value to the digital value. So here we can use the ADC sensors in our third phase, and after conversion of these things we implemented the ADCs. We implemented the values of the electric vehicle as acceleration, brake and motor temperature as well as SOC by Pixim lab, and get simulated in the IO virtual terms. In our 4 phases of our project, that is the EV dynamic model. In EV dynamic model we get studies about the speed, torque, state of charge, range, regeneration, brake and everything. So in the EV dynamic models, electric vehicle dynamic model, here we created the speed, we generate the torque, we give the SOCs and everything from the Pixim lab, and get simulated in the IO virtual terms to obtain the real verification of our code and everything. In our fifth phase of our projects, in our fifth project, what happened? In this we have found that HCSR04 is the ultrasonic sensor which help us to find the distance of the object from the another object. That is helpful for the electric vehicle for any collision, because suppose it can detect the things from the time to collision, blind spot detection and everything. That is the next vehicle in the front of the our objects, or in the side, left as well as right. So these are detect our electric vehicle that from the injury or from the safety. So this ultrasonic sensor with that is a very helpful. In our fifth phase we created this thing. In our sixth phase, fault and alarm system, that's helpful for the any electric vehicle that creates the sounds with the help of ultrasonic sensor, because these four level of alarm priority has to find the driver better safety, because this fault and alarm system, as we created the project as the advisory alarm as well as critical alarm. So there is two alarms which creates the sound when ultrasonic sensor detects the less distance required in comparison to the minimum, um, in comparison to the minimum, yeah, average distance which is needed to make the distance from one vehicle to another. So here we created this thing in our sixth phase. When we go to the our seventh phase, we have found UR telemeter. UR telemeter, that is the UR stands for uniform asynchronous receiver and transmitter. In this we have created the structure frame of SPD, SOC, TRQ, TMP, RNG and such these things. And after in our 8th phase UART cell, that is the live parameter injection via the serial command. It's mean that what we have to implemented before in the Pixim lab, we have integrate all the things, and take the live parameter injection via the serial command. So these are the completed in our the 8th phase, and at the last we have to integrate all the things what we have to completed in our phase number 1 to phase number 8, and setup of the Python dashboard as the matplotlib, and at the last we have to get the simulation of speedometer, ADAS, bird eye, SOC bar and everything. When we go to in our fourth slide, what happened in our fourth slide, that's the things we have to uh, discussed in later, that in phase number 1 and 2, when we talk about the environment setup and GUI peripherals. Here there is the first there is the installation of STM32Cube for the purpose of STM32 firmware programming. Second, the Pixim Lab STM32 Blue Pill simulation. In third, the Python 3 plus PIP dashboard plus library, Matplotlib, NumPy, live visualizations. And here in the phase number 2, what happened, peripheral configuration such as the timer, interrupt, SCSR04 timing, which is used for the ultrasonic echo capture, buzzer, PWM, ADC channel that requires the acceleration, brake, motor temperature, SOC from the pin number PA02, PA1, PA2, and these all the things, GOPI output, for finding out the collision, blind spot detection, fault alarms and advisory critical alarms and every things. At the last US art one, that's Pixim virtual term that help us to connect the distance of for the serial command. In our phase number 3 and 4, in our phase 3 and 4, in 3 ADS sensor system plus 4 at the AEV dynamic models, the goal is STM32 reads the analog inputs and simulates the EV physics. So in phase number 3 AD, see sensor input PA0 acceleration pedal, PA1 brake pedal, PA2 motor temperature, and here we write the ADC conversion that need the 12 bit for our projects from 0 to 4095 with the scaled engineering unit. And when we come to the phase number 4 EV dynamic engine, we find the motor torque 0 to 250 nanometer mode scaled regenerating brake for 80 nanometer speeds, that is integrate the torque by mass SO state of the charge for the 20 km per hour batteries range in the ecosystem drive mode eco normal and sport, and these all the regenerating brake greater than 5% at the speeds. When we come about the six slides in phase number 5, ultrasonic ADAS engine HCSR04 sensor that need FCW, BSN, BSD or TTC. TTC require the time to collision, BSD tells us about the blind spot detection, and FCW that is the front collision width. So here we need the sensor layout, bird eye, that is tells us about the EV's electric vehicle. Left, right, and front is denoted as the three different colors that shows how we can protect our electric vehicles. So there is some distance FCW less than 50 centimeter, FCW critical less than 20 centimeter, BSD active less than 30 centimeter, and speed greater than 20 km per hour, and TTC warning less than 3 seconds. So FCW the forward collision warning, TTC time to collision, BSD blind spot detection, PA parking assistance, and OS over speed advisory. So these are all the things we have to implemented in our projects. These are our basic understanding. When we come to about slides number 7, phase number 6. So fault detection alarm priority. In this, what happened? We have to put the fault conditions in the basis of trigger condition. When the motor temperature is greater than 90 degrees Celsius, fault 0 T, battery SOC less than 2%, fault SOC, collision critical less than 20 centimeter, fault underscore COL, a fault underscore SEN, ultrasonic sensor timeout, and fault underscore com UART com timeout. These four level alarm priorities: the alarm none, alarm advisory, alarm warning, and alarm critical. So these all are the basic terminology of alarm priorities that helps any electric vehicles to protect from any injuries or accidents. When we come about the slides number 8, you are telemeter protocol. In this in the unit line number 1, the electric vehicle telemeter frame, that is a printed every 10 into 10 meter seconds is equals to 100 meter second. In line number 2, ADAS frame, advanced driver assistance signal, printed every 100 millisecond sensor tick. So in the field reference SPD, vehicle speed, SOC state of charge, TRQ motor torque, TMP motor temperature, RNG estimate range, and everything front, left, right, that is ultrasonic distance. The everything what we have to implement it before, we have to connect the every one to each other from the UART. That is the serial command communication, serial command communication. So TTC time to collision, COL collision level 0 to 2, BSD blind spot, ALM alarm priority, FLT fault byte. So these all the things here in 9. UART cell in phase number 8, UART cell live parameter injection. Why UART cell? Because inject the specific speed, validate alarm threshold without moving physical potentiometer, simulate battery drain, over temperature and fault conditions, switch drive mode, eco, normal, and spot via serial terminal, reset fault, and observe system recovery behaviors. So all the things that's the supported the cell command is speeds kilometer per hour, set vehicle speed directly, SOC set battery state of charge, temperature set motor temperature, mode eco, normal sports, and reset status and fault. These all are the serial command that is provided to test and debug the STM32 framework without the hardware changing. And in slide number 10, what happened? Phase number 9, the Python matplotlib dashboard, real-time electric vehicle advanced visualization at 10 fps, 100 millisecond animation interval. So what happened is speedometer, circular arc gauge, color changes green, orange, red, and needle plus large numeric readout, that is the condition of a speedometer in the battery SoC, horizontal bar with the live percentage plus estimated range, drive mode level, eco, normal and sports shown below. Speed history 60, sample rolling line chart of vehicle speed and everything. So electric vehicle matrix, info panel the torque, acceleration, brake, motor temperature, alarm level, fault code, UART, signals status, ADAS, bird eye, top down lane view, ego car, front obstacle, BSD, TTC. So these are all the things we have to complement it, and we have to simulate the everything in the Python dashboard, and we have successfully execution of this project in our next slide 11. These are the flow of our project. First the read ADC, second the EV update, ADAS update, trigger SC SR04, make eco distance, commute TTC, FCW BSD level, set alarm priority, drive the LED, build UART frame, send the via UART UART serial, 11th Python phrase line, update the state dictionary, and at the last we have to implement it in the Python dashboard. So there are the successfully execution of our project by using these slides, and hence we have to successfully completed this internship. This internship was a valuable learning experience for me, and I gained the practical knowledge, developed the new technical skills, and improved my understanding of real world industry practice. Overall, it was highly beneficial for my professional as well as personal growth. Thank you.